Hello there, and welcome to Simple Sleepy Science. Right now, above you, the moon is pulling. Not just floating there, actually pulling. On the oceans, on the ground beneath your feet, on the water inside your own body. It's been doing this for over 4 billion years, and tonight we're going to explore what that gentle pull really means. The moon sits about 240,000 miles away, yet its gravity reaches across all that empty space and lifts entire oceans. Twice a day, the seas rise and fall because of this invisible hand. It's one of the most peaceful forces in nature, and it's happening right now while you settle in. So, get comfortable. Let your body relax. We're going somewhere quiet tonight to understand the rhythm that's older than almost anything on Earth. If this brings you calm, if you enjoy these quiet journeys through science, consider subscribing to Simple Science for Sleep. You'll join thousands of others who love falling asleep to these stories. And leave a comment letting me know where you're listening from and what time it is there. I love hearing from this community. The tides do more than just move water. They create something else, something that changed our entire planet. That gentle pull, repeated twice a day for billions of years, creates friction. The oceans rub against the seafloor. The continents drag through the water. And this friction does something remarkable. It slows Earth's rotation. Every day is getting slightly longer, just 1.7 milliseconds per century, but it adds up. When the moon first formed, Earth's days were only 6 hours long. Our planet was spinning fast, like a top that's just been released. But the moon's pull acted as a brake, gradually slowing us down. Over 4 billion years, our days stretched from 6 hours to the 24 hours we know now. The moon gave us time, literally. This same friction has another effect. As Earth's rotation slows, the moon moves farther away. It's like a figure skater pulling their arms in to spin faster, but in reverse. The moon is pulling its arms out, so to speak, and moving away from Earth. About 1.5 inches every year, the width of your thumb. It seems small, but over billions of years, the moon has been on a slow journey outward. Right now, the distance is just right. The moon appears almost exactly the same size as the sun in our sky, which is why we get perfect solar eclipses. In a few 100 million years, the moon will be too far away for this to happen. We live in a special time when the moon is at just the right distance to create one of nature's most beautiful coincidences. But the moon's pull creates more than tides and time. It creates stability, which we'll explore next, as we discover how this quiet companion gave Earth the gift of predictable seasons. The moon wasn't always there. 4.5 billion years ago, Earth was alone. A young planet, barely 100 million years old, spinning through space without a companion. Then something happened that would change everything. Another planet, about the size of Mars, was traveling through the early solar system on a collision course with Earth. Scientists call this planet Theia, after the Greek goddess who gave birth to the moon goddess. Theia had been forming in roughly the same orbit as Earth, and eventually, gravity brought them together. The impact was unimaginably violent. Theia hit Earth at about 10,000 miles per hour. But here's what makes this collision special. It wasn't head-on. Theia struck at an angle, like a glancing blow. This matters because a direct hit would have destroyed both planets completely, turning them into scattered debris. The angled impact was just right. When Theia hit, it didn't punch through Earth like a bullet. Instead, it merged. The two planets' outer layers exploded into space as superheated rock and metal. Some of Theia's core probably sank into Earth's core, mixing with our planet's molten center. But the outer material, the crust and mantle, was thrown outward in a massive spray of debris. Picture Earth right after the impact. The entire surface was an ocean of molten rock, glowing red hot. Above it, a ring of debris circled the planet. Chunks of rock ranging from pebbles to mountains, all orbiting together. The ring probably looked like Saturn's rings, but made of molten stone instead of ice. This debris ring was unstable. Pieces crashed into each other. Larger chunks pulled in smaller ones through gravity. Over time, maybe just a few thousand years, the debris began clumping together. The largest clump kept growing, sweeping up more and more material from the ring. This became the moon. The newborn moon was nothing like the cool grey sphere we see today. It was molten, a ball of liquid rock, glowing bright from the heat of formation. Its surface was an ocean of magma, hundreds of miles deep. There was no solid ground, just churning liquid stone. The moon had to cool for millions of years before a crust could form. And it was close, so close. The moon formed only about 15,000 miles from Earth, roughly where our communication satellites orbit today. From Earth's surface, it would have filled a huge portion of the sky, appearing 15 times larger than the moon we see now. The tides it created must have been enormous, with waves of molten rock rising and falling on Earth's magma ocean. Over millions of years, the moon's surface slowly cooled. The magma ocean crystallized from the bottom up. Lighter minerals floated to the top, forming the moon's bright highlands. Denser materials sank to form the interior layers. Gradually, the moon developed a crust, a mantle, and a small core. But even as it cooled, the moon was already moving away. That same tidal friction we talked about earlier was pushing it farther from Earth. The moon's been on a slow journey outward from the moment it formed. From 15,000 miles away to the 240,000 miles it sits at today. This violent birth explains something important about the moon. It explains why the moon's composition is similar to Earth's outer layers, why it has less iron than Earth does overall, why it's less dense. The moon is literally made from Earth's crust and mantle, mixed with pieces of Theia. When you look at the moon, you're looking at a piece of Earth's history, thrown into space and reformed into a new world. The collision also explains Earth's unusual tilt. Most planets spin fairly upright, but Earth leans at 23.5 degrees. Theia's impact knocked us sideways, and we've stayed tilted ever since. And this tilt, held steady by the moon's presence, is what gives us our seasons. That tilt became crucial, but first, let's talk about distance. When the moon formed at 15,000 miles away, everything on Earth moved faster. The planet spun like a top, completing a full rotation in just 6 hours. Sunrise to sunrise, in the time it takes to watch a movie. The moon loomed enormous in the sky. If you could have stood on Earth's cooling surface and looked up, the moon would have appeared about 15 times larger than it does today. It would have covered a huge arc of the sky, dominating the view. And it was bright. So much surface area reflecting the sun's light that nights were never truly dark. The tides were extreme, not just water tides, because Earth's oceans hadn't formed yet, but tides in the molten rock itself. The entire surface of Earth bulged toward the moon and away from it. Waves of magma hundreds of feet high rolled across the planet twice every 6-hour day. The ground itself rose and fell like a slow, massive breath. As millions of years passed, the moon moved outward. Each year, it crept a little farther away. The mechanism is elegant. Earth's rotation carries the tidal bulge slightly ahead of the moon. This bulge has mass, and its gravity pulls the moon forward in its orbit. When you pull something forward in orbit, it moves to a higher, slower orbit. So the moon spiraled outward, gradually, steadily. At the same time, Earth slowed down, the tidal friction acting as a brake. The moon's gravity pulling back on Earth's spinning tidal bulges. Energy transferred from Earth's rotation to the moon's orbit. As Earth lost rotational energy, days grew longer. As the moon gained orbital energy, it moved farther away. The two changes are connected, like two sides of the same coin. By 3 billion years ago, the moon was about 180,000 miles away. Still closer than today, but the difference was shrinking. Days had stretched to about 18 hours. The moon appeared about 30% larger in the sky than it does now. Tides in Earth's new oceans were stronger, surging higher up the shores. Ancient rocks preserve evidence of this. Tidal rhythmites are layered sediments deposited by tides. Scientists can count the layers like tree rings. Each thin layer represents one tide. By counting layers between thicker bands that mark longer cycles, researchers can figure out how many tides happened per day, per month, per year. The Bedtime math reveals how long days were and how far away the moon was when those rocks formed. The evidence shows the pattern clearly. 900 million years ago, a year had about 481 days, meaning each day was roughly 18 hours long. 620 million years ago, a year had about 400 days, making each day about 22 hours long. The numbers line up perfectly with the moon's gradual retreat. This retreat continues today. Modern measurements using laser reflectors left on the moon by Apollo astronauts show the moon is moving away at exactly 1.48 inches per year. Scientists shoot laser pulses at mirrors on the moon's surface and measure how long the light takes to return. By comparing measurements over years, they can detect the moon's movement with incredible precision. That 1.5 inches per year adds up. Over Earth's history, the moon has moved from 15,000 miles to 240,000 miles. It's traveled more than 225,000 miles through space, slowly unwinding from Earth like a weight on a string. And it's still going. But here's the beautiful part. This slow separation gave Earth something precious. As the moon moved away and days grew longer, Earth's rotation stabilized. The moon's gravity locked Earth's tilt at 23.5 degrees, preventing wild wobbles that would have made the climate chaotic. Without the moon, Earth would tumble. Our axis would wobble wildly over millions of years, swinging anywhere from nearly upright to tilted on its side. Mars shows us what happens. Mars has 2 tiny moons, basically captured asteroids, too small to provide stability. Mars's tilt changes from 15 degrees to 35 degrees over cycles lasting about 100,000 years. When Mars tilts at 15 degrees, its seasons are mild. The poles get some sunlight year-round. But when it swings to 35 degrees, the seasons become extreme. During summer, one pole points almost directly at the sun, baking under constant daylight. During winter, that same pole freezes in months of darkness. The climate swings wildly, unable to settle into any pattern. Earth could have been the same way. Our tilt should be unstable. We're the right size and distance from the sun for our axis to wobble significantly. But the moon prevents this. Its gravitational pull on Earth's equatorial bulge acts like a gyroscope stabilizer, keeping us locked at 23.5 degrees. The tilt does vary slightly, moving between 22.1 and 24.5 degrees over 41,000 years. But that's a tiny range. The moon keeps us steady. This stability gave life a gift. Predictable seasons. Spring always comes. Summer follows. Autumn arrives on schedule. Winter passes. The cycle repeats, year after year, century after century, for hundreds of millions of years. Plants could evolve to match these rhythms. Animals could time their migrations, their breeding, their hibernation to the reliable pattern. Think about a tree. It drops its leaves in autumn, preparing for winter. It stays dormant through the cold months, conserving energy. In spring, it blooms again, timing its growth to the warming temperatures. This only works because seasons are predictable. If winter came randomly, lasting anywhere from a few months to several years, the tree couldn't survive. It wouldn't know when to bloom or when to prepare for cold. The same applies to animals. Birds migrate south for winter because they know winter is coming and when it will arrive. Monarch butterflies travel thousands of miles to reach their wintering grounds at exactly the right time. Bears hibernate because they can count on food being scarce for a specific period. Frogs freeze solid in winter and thaw in spring because spring reliably returns. Even the oceans depend on seasonal stability. Ocean currents are driven partly by seasonal temperature changes. Nutrients cycle from deep water to the surface on predictable schedules. Plankton blooms happen in spring when sunlight returns and nutrients are available. These blooms feed fish, which feed larger fish, which feed seabirds and marine mammals. The entire ocean food web depends on timing that the moon makes possible. For humans, stable seasons meant agriculture could develop. You can only farm if you know when to plant and when to harvest. Ancient farmers learned to read the seasons, watching the sky for signs of spring. They planted when the ground thawed and harvested before winter returned. This predictability allowed civilizations to form, cities to grow, and complex societies to develop. The moon didn't just give us tides and longer days. It gave us stability, a world where the future resembles the past, where life can plan ahead, adapt to cycles, and build complexity over time. Without the moon, Earth might still have life, but it would be simple life, unable to depend on anything staying the same. And there's something else the moon does, something most people never think about. When you look up at the moon, you always see the same face, the same patterns of light and dark. This isn't coincidence. The moon is locked to Earth. It rotates once on its axis in exactly the same time it takes to orbit Earth once. Both take 27.3 days. This means the same side always faces us. We call the side we never see the far side, though most people call it the dark side. That name is misleading. The far side gets just as much sunlight as the near side. During a new moon, when the side facing us is dark, the far side is in full sunlight. During a full moon, when our side is bright, the far side is in darkness. The far side isn't dark, it's just hidden from our view. This locking happened because of tides, not water tides, but tides in the moon's solid rock. Billions of years ago, the moon rotated faster. It showed us different faces throughout the month. But Earth's gravity pulled on the moon's tidal bulges, creating friction that slowed its rotation. Eventually, the moon's rotation slowed down until it matched its orbital period perfectly. The tidal bulge lined up with Earth and stayed there. Most large moons in the solar system are tidally locked to their planets. It's the natural end state when a small body orbits close to a larger one. The process takes time, but given enough millions of years, the smaller body always locks. Earth will eventually become tidally locked to the moon too, but that would take billions of years. Humans didn't see the far side until 1959, when a Soviet spacecraft flew past and took photographs. What those images revealed surprised everyone. The far side looks completely different from the near side. The near side has large, dark patches. The Maria we see as the man in the moon or the rabbit, depending on your culture. The far side has almost none of these dark areas. It's mostly bright, heavily cratered highlands. The difference is dramatic. The near side surface is about 31% Maria, those dark volcanic plains. The far side is only 2% Maria. Almost the entire far side is ancient, pale highland crust, pockmarked with craters. Scientists debated for years about why this difference exists. The answer involves Earth. The near side faces Earth and has always faced Earth. Earth's gravity created tidal heating in the moon's interior, focusing that heat toward the near side. When large asteroids struck the near side billions of years ago, the crust was thinner there, and magma could flow up more easily to fill the impact basins. On the far side, the crust was thicker and colder. When asteroids hit there, the crust was too thick for magma to break through. There's also a thickness difference. The far side's crust averages about 40 miles thick. The near side's crust is about 30 miles thick. This 10-mile difference was enough to change the moon's entire appearance. The far side has one massive feature: the South Pole Aitken Basin, one of the largest impact craters in the solar system. It's 1,600 miles across and more than 5 miles deep in places. An asteroid the size of a small planet hit the far side about 4 billion years ago with enough force to nearly punch through the moon's crust. Yet, even this enormous impact didn't create a lava-filled mare. the crust was too thick, and the impact happened too late, after the moon's interior had cooled too much. The far side remains a mystery in many ways. It's heavily cratered because it faces away from Earth, so Earth can't shield it from asteroid impacts the way the moon shields Earth. Every asteroid that might have hit Earth from that direction hit the far side instead, leaving its mark in the ancient surface. Those dark patches have names: Mare Tranquillitatis, Mare Serenitatis, Mare Imbrium, the Sea of Tranquility, the Sea of Serenity, the Sea of Rains. Ancient astronomers thought they were actual oceans of water. They pointed their early telescopes at the moon and saw smooth, dark areas that looked like seas, surrounded by bright, rough areas that looked like land. The names stuck, even after we learned the truth. The Maria aren't water. They're basalt, a type of volcanic rock. Dark, dense, and smooth. The same kind of rock that forms when lava flows from Hawaiian volcanoes and cools. But the moon's Maria are ancient. Most formed between 3.1 and 3.9 billion years ago, during a period scientists call the Late Heavy Bombardment. During this time, the inner solar system was being cleaned out. Asteroids and comets that hadn't yet settled into stable orbits were crashing into planets and moons at a furious rate. Large asteroids slammed into the moon, punching deep craters into its crust. The impacts were so powerful, they cracked the crust and created basins dozens of miles deep. The moon's interior was still hot then, not molten like it had been billions of years earlier, but warm enough that magma existed deep underground. When an asteroid impact cracked the crust and created a deep basin, magma had a path to the surface. It flowed up through the cracks like blood from a wound, filling the impact basin with liquid rock. The lava didn't erupt explosively like some Earth volcanoes do. The moon has no atmosphere, so there's no gas to create pressure. Instead, the lava simply flowed out, spreading across the basin floor in vast sheets. Some flows were hundreds of miles wide and dozens of feet deep. They filled the basins layer by layer, sometimes over millions of years. As the lava cooled, it turned dark. Basalt contains iron and magnesium, which give it that characteristic dark grey to black colour. The smooth lava surface contrasted sharply with the bright, rough highland crust surrounding it. From Earth, these dark plains looked like seas. Mare Imbrium, the Sea of Rains, is one of the largest. The asteroid that created it was probably 150 miles across. The impact excavated a basin 700 miles wide. Lava filled it to a depth of several miles in some places. You can see Mare Imbrium easily with just your eyes. It's the dark area that forms the right eye if you see a face in the moon, or part of the rabbit if you see that shape instead. Each mare tells a story of violence followed by healing. The asteroid impact was catastrophic, melting and throwing out rock, creating earthquakes that shook the entire moon. But then came the quiet part. The lava flows, slowly filling the wound, smoothing it over, creating a new surface. The Maria are scars that healed. The youngest large mare is Oceanus Procellarum, the ocean of storms. Parts of it are only 1.2 billion years old, which is young by moon standards. It's also unusual because it's not a circular impact basin. Instead, it formed in a region where the crust was naturally thinner, allowing magma to seep up through multiple vents over a long period. The volcanic activity stopped billions of years ago. The moon's interior cooled below the point where magma could form. The last lava flows solidified, and the Maria became frozen in time. Now they're just flat plains of ancient basalt, dark and smooth, waiting silently under the sun and stars. And on those plains, there are footprints. Well, humans have walked on the moon. Between 1969 and 1972, Apollo astronauts left their bootprints in the lunar dust. Those prints are still there, exactly as they were left. Sharp edges, clear treads, perfectly preserved. On Earth, a footprint in sand lasts until the next wave or gust of wind. A footprint in mud might last a few days before rain washes it away. But the moon has no wind, no rain, no weather at all. The footprints will remain for millions of years, maybe longer. They'll outlast most things humans have built on Earth. The only thing that changes the moon's surface is time itself, working incredibly slowly. Tiny meteorites, most smaller than grains of sand, constantly hit the moon. They strike at thousands of miles per hour, vaporizing on impact and kicking up tiny amounts of dust. This process, called space weathering, gradually softens sharp edges and mixes the surface layer. But it's slow. Calculations suggest it would take tens of millions of years for space weathering to erase a footprint completely. The Apollo landing sites will look essentially the same for longer than humans have existed as a species. When those bootprints finally fade, it will be because the moon itself has worn them away atom by atom. The moon's surface changes in other ways too, just as slowly. Temperature swings crack rocks over time. During the lunar day, which lasts about 2 Earth weeks, temperatures climb to 250 degrees Fahrenheit. During the lunar night, equally long, temperatures drop to negative 250 degrees. This 500-degree swing happens every month, and over millions of years, it causes rocks to fracture and break apart. But even this process is gentle compared to Earth. No water seeps into cracks and expands when it freezes. No plant roots work their way between rock layers. No animals burrow or dig. The moon's rocks break apart purely from temperature stress, and it takes a very long time. Larger meteorites do hit occasionally. These create new craters, throwing dust and rock across the surface. A meteorite impact near an Apollo landing site could cover the footprints with a layer of ejecta. But space is vast, and the moon's surface is large. The odds of a significant impact hitting any specific spot are extremely low. Scientists have calculated that the Apollo landing sites have about a 1% chance of being struck by a crater-forming meteorite in the next million years. That means there's a 99% chance the sites will remain undisturbed. The footprints, the equipment left behind, the flags, the rovers, all have excellent odds of lasting for geological timescales. This preservation is unique in our solar system. Mars has wind that erases surface features. Venus has an atmosphere so thick and hot it would destroy anything on its surface. Jupiter's moons are geologically active, resurfacing themselves. Saturn's moon Titan has rain and rivers. Only the moon offers this kind of perfect, timeless preservation. The Apollo astronauts didn't just leave footprints. They left scientific instruments, TV cameras, tools, and parts of their lunar modules. All of it remains, frozen in time. The flags they planted have probably been bleached white by decades of unfiltered solar radiation, but they're still standing. The rovers are still parked where they were left, waiting silently. In a way, the moon is the universe's museum. Everything that touches its surface becomes part of a permanent collection. And the surface itself, the dust the astronauts walked through, has its own strange story. The dust is unlike anything on Earth. Scientists call it regolith, and it covers the entire moon to a depth of several feet in most places. It looks grey and fine like powder, but touch it and you'd find it sharp and abrasive. Every grain is jagged, like tiny shards of broken glass. On Earth, sand and dust become smooth through erosion. Wind tumbles the grains against each other. Water rolls them along riverbeds. Over time, the sharp edges wear away and particles become round. But the moon has no wind or water. The regolith forms when meteorites pulverize rock, and the fragments stay exactly as sharp as the moment they broke. Apollo astronauts reported that the dust clung to everything. Their spacesuits became coated in it. It stuck to their gloves, their boots, their equipment. When they brought it inside the lunar module, it floated in the air and wouldn't settle. The dust has static electricity because it's constantly bombarded by charged particles from the sun. This charge makes it cling to surfaces like hair clinging to a balloon. The dust also has a smell. Multiple astronauts described it as similar to gunpowder or spent ammunition. The smell appeared when they removed their helmets after moonwalks. Scientists think the smell comes from chemical reactions. The dust contains tiny amounts of metallic iron, created when meteorites vaporize the surface. This iron oxidizes when exposed to the moisture and oxygen inside the spacecraft, creating the distinctive odor. Breathing lunar dust would be dangerous. The sharp particles could damage lung tissue. The dust is so fine that normal air filters wouldn't stop it. During Apollo missions, astronauts tried to brush it off before entering the lunar module, but they could never remove it completely. Future moon bases will need special airlocks and cleaning systems to deal with the dust problem. The regolith varies in depth. In the Maria, the smooth lava plains, it's typically 10 to 15 feet deep. In the highlands, where the surface has been exposed to impacts for billions of years longer, it can be 30 feet deep or more. The very top layer, maybe the first millimeter, is even finer than the rest, pulverized by micrometeorites into powder that behaves almost like liquid. When astronauts walked on the moon, their boots sank about an inch into this surface layer. It compressed under their weight, but didn't scatter or blow away. Rover wheels created tracks that look almost wet, with crisp edges and smooth walls. The dust packed down rather than spraying out to the sides. Each grain of regolith contains history. Some particles are pieces of basalt from the Maria. Others are bits of ancient highland crust. Some contain fragments of meteorites from asteroids that traveled across the solar system before striking the moon. A handful of lunar dust is a mixture of the moon's entire 4 billion year story. The regolith also contains something surprising: tiny glass beads. When meteorites hit the surface at high speed, the impact melts the rock instantly. This molten material sprays out as droplets that cool and harden while still in flight, forming perfect spheres of glass. The regolith is full of these beads, most smaller than grains of sand, scattered like microscopic marbles through the dust. This strange, sharp, clingy dust exists because the moon has no atmosphere. Without air, everything about the moon becomes more extreme. The moon has no atmosphere worth mentioning. Earth's atmosphere weighs about 5 quadrillion tons. The moon's entire atmosphere weighs about 10 tons, less than 2 elephants. It's so thin that for practical purposes, the moon is in a vacuum. This creates extreme temperature swings. On Earth, our atmosphere acts like a blanket, trapping heat at night and providing shade during the day. The moon has no such protection. When the sun rises over a spot on the moon, temperatures climb steadily for 2 weeks until they reach about 250 degrees Fahrenheit, hot enough to boil water. When the sun sets, temperatures plummet over the next 2 weeks to negative 250 degrees, cold enough to freeze carbon dioxide solid. Stand on the moon in sunlight, and your suit would need to reflect heat away to keep you cool. Step into shadow, and it would need to generate heat to keep you warm. The difference between light and shadow is 5 degrees. On Earth, stepping from sunlight into shade might feel 10 or 15 degrees cooler. On the moon, it's the difference between an oven and a deep freezer. The lack of atmosphere means no sound travels. Sound needs molecules to vibrate. On Earth, sound waves move through air molecules, traveling from the source to your ear. On the moon, there are no molecules between you and anything else. You could stand next to a meteor impact and hear nothing. The ground would shake and transmit vibrations through your boots, but the explosion itself would be silent. Apollo astronauts couldn't talk to each other outside unless they used radios. Even standing face to face, their voices couldn't cross the gap between helmets. They communicated through radio waves, which don't need air to travel. Inside the lunar module, with air to carry sound, they could speak normally again. No atmosphere also means no weather. No clouds, no rain, no snow, no wind to blow the dust around. The moon's surface looks the same today as it did 1 million years ago, minus a few new meteorite craters. Weather is just air, moving and changing, and the moon has nowhere to move. Without an atmosphere, there's no protection from meteorites. On Earth, small meteorites burn up in the atmosphere, creating shooting stars. Only the largest ones survive to hit the ground. On the moon, every meteorite, no matter how small, makes it to the surface. A grain of sand traveling at 20,000 miles per hour hits with the force of a bullet. The moon's surface is constantly being sandblasted by these tiny impacts. The lack of air also means perfect preservation. On Earth, oxygen causes rust, water causes decay, microbes break down organic material. None of these processes happen on the moon. The American flags planted by astronauts haven't rusted or rotted. They've only faded from solar radiation. Metal doesn't corrode. Plastic doesn't degrade from weathering. Everything stays chemically stable. The thin atmosphere the moon does have comes from several sources. Some atoms are knocked off the surface by solar wind. Some are released from the interior through tiny cracks. Comets that impact the moon add trace amounts of water vapor, but all these sources combined create an atmosphere so thin that if you could somehow collect all of it, it would fit in a small building. This vacuum environment makes the moon look different than it would with air. There's no haze, no scattering of light. The sky is always black, even during the day. Stars are visible in full sunlight because there's no atmosphere to create a blue sky and wash them out. And the moon itself appears differently when seen from its surface. The moon doesn't make its own light. It's a cold, dead rock reflecting sunlight. But here's what surprises most people. The moon is actually quite dark. Its surface reflects only about 12% of the sunlight that hits it. For comparison, that's about as reflective as worn asphalt on an old road. Earth is much brighter. Our planet reflects about 30% of sunlight, more than twice as much as the moon. This is because Earth has clouds, ice, and oceans that bounce light back into space. The moon has none of these, just dark grey rock and darker grey basalt. Yet from Earth, the moon looks brilliant in the night sky. It looks bright because it's the only thing up there catching sunlight. Your eye compares it to the black sky around it, and by contrast, it seems to glow. But if you could put a piece of the moon next to a piece of white paper, the moon would look dark grey, almost charcoal. From the moon's surface, Earth would be the brightest thing in the sky. Astronauts on the moon saw Earth hanging in the black sky, blue and white and stunning. Earth appears about 4 times larger than the moon appears from Earth, and it reflects more light per square inch. The view would be breathtaking. When the moon is new from our perspective, the side facing us is dark. But from the moon's perspective, Earth is full, shining bright. This light from Earth reflects off the moon's surface and back to us. We call it Earthshine, and you can see it if you look carefully at a crescent moon. The dark part of the moon isn't completely black. It's faintly lit by Earth's reflected light, giving it a subtle glow. Earthshine is stronger than moonlight, much stronger. If you were standing on the moon during Earth's full phase, the light would be bright enough to read by. Earth's atmosphere and oceans make it reflective enough to illuminate the moon's night, which then reflects some of that light back to Earth, completing the circle. The moon's brightness changes depending on its phase. During a full moon, it can cast shadows on Earth. It's bright enough to see colours, though they appear muted. During a crescent moon, it provides just enough light to see basic shapes. The difference is dramatic, not just because less surface is visible, but because of how light reflects off the moon's rough surface. The moon is brightest when it's full because of something called the opposition effect. When the sun is directly behind you as you look at the moon, shadows disappear. Every crater, every rock, every tiny bump casts its shadow away from you, hidden behind itself. The surface appears brighter because you're not seeing any shadows, only sunlit surfaces. As the moon moves through its phases, shadows appear and the brightness drops. For millions of years before humans created artificial light, the moon was the night's only lamp. People traveled by moonlight. Armies planned campaigns around full moons when they could march at night. Fishermen timed their voyages by the moon's cycle. The difference between a moonlit night and a moonless night could mean life or death. Even today, in places without electric lights, the moon still serves this ancient purpose. It rises and sets according to its phase, sometimes appearing during the day, sometimes at night, following a cycle that's completely separate from the sun's daily rhythm. The moon's phases are just shadows. As the moon orbits Earth, the angle between the sun, moon, and Earth changes. We see different amounts of the moon's sunlit side. That's all it is. Simple geometry, creating the cycle we've watched for as long as humans have existed. Start with new moon. The moon sits between Earth and the sun. The sunlit side faces away from us. We see the dark side, which means we don't see the moon at all. It's up during the day, crossing the sky with the sun, invisible against the bright sky. A few days later, the moon has moved in its orbit. A sliver of the sunlit side becomes visible from Earth. This is the waxing crescent. The moon now sets shortly after sunset, visible in the western sky as a thin, bright curve. The rest of the moon's face is often visible too, faintly lit by earthshine. After about a week, the moon has traveled a quarter of the way around Earth. Now we see exactly half of the sunlit side. This is first quarter, though it looks like a half moon. The moon rises around noon and sets around midnight. It's high in the sky at sunset, offering light through the evening. The moon continues its journey. More of the sunlit side becomes visible each night. Waxing gibbous, more than half, but not yet full. The word gibbous comes from Latin, meaning humpbacked. The moon rises in the afternoon now and sets after midnight, visible most of the night. After 2 weeks, the moon reaches the opposite side of Earth from the sun. The entire sunlit side faces us. Full moon. It rises at sunset and sets at sunrise, traveling across the sky all night. This is when the moon is brightest, lighting the night world below. Then the cycle reverses. The moon continues its orbit, and the sunlit portion we see begins to shrink. Waning gibbous, still more than half, but decreasing. The moon now rises after sunset and stays visible into the morning hours. After 3 weeks, the moon has traveled 3/4 of the way around Earth. Once again, we see exactly half the sunlit side, but now it's the opposite half from first quarter. This is third quarter, also called last quarter. The moon rises around midnight and sets around noon. The final phase is waning crescent, a thin curve of light visible in the eastern sky before sunrise. The moon is nearly back to its starting position, almost between Earth and the sun again. Soon it will be new moon, and the cycle begins again. The complete cycle takes 29.5 days. We call this a lunar month. It's not the same as the moon's orbital period, which is 27.3 days. The difference exists because Earth is also moving around the sun. The moon has to travel a bit extra to get back to the same position relative to both Earth and Sun. Ancient people organized their lives around this cycle. Many calendars were lunar, with months following the moon's phases. The Islamic calendar still works this way. Jewish holidays are timed to specific moon phases. The Chinese calendar combines lunar months with solar years. Our modern calendar mostly ignores the moon, but the old connection remains in our language. Month comes from moon. Monday is Moon Day. The moon's cycle is woven into human culture so deeply that we barely notice it anymore, even though it continues overhead, unchanging and reliable. Sometimes the moon turns red. This happens during a lunar eclipse, when Earth passes directly between the Sun and Moon. Earth's shadow falls across the moon's face, and instead of going dark, the moon glows copper red. The alignment has to be perfect. The Sun, Earth, and Moon must line up in a straight line. This only happens during a full moon, when the moon is on the opposite side of Earth from the Sun. But not every full moon creates an eclipse. The moon's orbit is tilted about 5 degrees relative to Earth's orbit around the Sun. Most months, the moon passes slightly above or below Earth's shadow. Only when the alignment is exact does the shadow catch the moon. Earth's shadow has 2 parts. The outer shadow, called the penumbra, is faint. When the moon enters this zone, it dims slightly, but doesn't change color. The inner shadow, the umbra, is darker. This is where Earth completely blocks the Sun's direct light. When the moon enters the umbra, the eclipse becomes obvious. You'd think the moon would disappear completely in Earth's full shadow, but it doesn't. It turns red instead. The reason is Earth's atmosphere. Sunlight hitting Earth's atmosphere bends as it passes through. The atmosphere acts like a lens, bending the light around Earth's edge into the shadow zone. This bent light is red. Earth's atmosphere scatters blue light, which is why our sky is blue. The blue light bounces away in all directions. Red light, with its longer wavelength, passes through the atmosphere more easily. During a lunar eclipse, all the red sunlight passing through Earth's atmosphere from every sunrise and sunset happening on Earth at that moment focuses on the moon. The moon's color during an eclipse depends on Earth's atmosphere. If the atmosphere is clear and clean, the moon appears bright orange-red. If Earth's atmosphere contains a lot of dust or particles, perhaps from recent volcanic eruptions, the moon appears darker, sometimes a deep brown or even nearly black. Scientists can learn about Earth's atmosphere by studying how red the moon appears during eclipses. Total lunar eclipses can last up to an hour and 40 minutes. The moon moves slowly through Earth's shadow, taking its time crossing from one side to the other. Unlike solar eclipses, which are brief and visible only from specific locations on Earth, lunar eclipses are long and visible from anywhere on Earth's night side. If you can see the moon, you can see the eclipse. Ancient people found eclipses terrifying. The moon's sudden transformation into a blood-red disk seemed like an omen. Many cultures believed a creature was eating the moon. The ancient Chinese thought it was a dragon. The Vikings believed it was wolves. The Incas thought it was a jaguar. People would make noise, bang drums, and shout to scare the creature away. Now we know eclipses are just geometry. The sun, earth, and moon playing their eternal dance, occasionally lining up just right to create this beautiful effect. Nothing supernatural, nothing dangerous, just light bending through air, painting the moon in shades of copper and rust. Lunar eclipses happen about twice a year on average, though some years have none, and some have 3. They're common enough that most people see several in their lifetime. Each one is different, with the moon taking on slightly different shades, depending on what's in Earth's atmosphere at that moment. The moon is slowing us down. Right now, as you rest, the moon's gravity is acting like a brake on Earth's rotation. The effect is tiny but constant. Each century, Earth's day gets about 1.7 milliseconds longer. You'd never notice it in a lifetime, but over geological time, it adds up dramatically. The mechanism is the same tidal friction we discussed earlier. Earth's rotation carries the tidal bulge ahead of the moon. The bulge has mass, and its gravity pulls back on Earth's rotation while pulling the moon forward. Earth loses rotational energy. The moon gains orbital energy and moves farther away. The two effects are linked like opposite ends of a seesaw. We can measure this by looking backward in time. Ancient coral fossils show daily and yearly growth rings, like trees. By counting the rings, scientists can determine how many days were in a year when that coral was alive. 400 million years ago, a year had about 400 days. Each day was roughly 22 hours long. The year hasn't changed length because Earth's orbit around the Sun is stable, but the day has stretched. Going back further, the effect becomes more dramatic. 620 million years ago, days were about 21.9 hours. 900 million years ago, about 18 hours. When complex life was just beginning, when the first animals were evolving in the oceans, the sun rose and set in less time than it takes to watch 2 movies. When dinosaurs walked Earth, days were about 23 hours long. The difference seems small, but it meant the Earth completed about 370 rotations per year instead of our current 365. Dinosaurs experienced more sunrises and sunsets in their lives than we do, even though their years were the same length as ours. The moon was closer then too, about 20,000 miles closer during the age of dinosaurs. It appeared slightly larger in the sky, though not enough to notice without careful measurement. The tides it created were stronger, pushing and pulling the oceans with more force than today. This process continues. In the far future, if given enough time, Earth's day would eventually equal a lunar month. Earth would become tidally locked to the moon, just as the moon is locked to Earth. One side of Earth would always face the moon. One side would never see it. This is the stable end state of the tidal interaction. But this won't happen. The process takes about 50 billion years, and the sun will die long before then. In about 5 billion years, the sun will expand into a red giant, possibly swallowing both Earth and moon. The tidal locking will never complete. The moon will keep slowly moving away, and Earth will keep slowly rotating slower, but neither will reach their final equilibrium. For now, we're in the middle of this process. Earth spins fast enough to create a 24-hour day. The moon orbits at a comfortable distance. The system is balanced, but still changing, like a pendulum that's been swinging for billions of years and will swing for billions more. Every night, the moon pulls itself a tiny bit farther away. Every day lasts a tiny bit longer than the day before. The changes are invisible on human timescales, but they're written into the rocks, into the fossils, into the very fabric of time itself. The moon is reshaping Earth's relationship with time, gradually and patiently. The moon's gravity isn't uniform. There are spots where gravity is slightly stronger, pulling more than surrounding areas. Scientists call these mascons, short for mass concentrations. They're invisible, but measurable, and they've caused problems for spacecraft orbiting the moon. Mascons exist beneath the Maria. When those giant asteroids hit the moon billions of years ago, they punched through the crust and exposed the denser mantle beneath. Then lava flowed up and filled the basins. The result is a region with more mass packed into the same volume. More mass means stronger gravity. The difference is small. A mascon might increase local gravity by about 0.06%. That's tiny on a human scale. You wouldn't notice it if you stood there. But for a spacecraft orbiting the moon at precise speeds and altitudes, it's significant. The spacecraft speeds up slightly as it passes over a mascon, then slows down as it leaves. Over multiple orbits, these small changes accumulate. Early lunar orbiters discovered mascons the hard way. Mission planners calculated orbits assuming the moon's gravity was uniform. The spacecraft entered orbit successfully, but over time, their paths changed. Some crashed into the moon sooner than expected. Others were pulled into unstable orbits. Scientists had to figure out what was going wrong. They mapped the moon's gravitational field by tracking how spacecraft orbits deviated from predictions. Wherever an orbit changed, there was a gravitational anomaly. The pattern matched the Maria perfectly. Every large mare had a mascon beneath it. The Maria weren't just visual features. They were gravitational landmarks. The strongest mascons lie under Mare Imbrium, Mare Serenitatis, Mare Crisium, and Mare Orientale. These are the youngest large impact basins, filled with the most lava. Older basins have weaker mascons because the moon's crust has had more time to adjust, slowly relaxing and reducing the gravitational difference. Modern spacecraft account for mascons in their flight plans. Lunar orbits require constant small adjustments to stay stable. The spacecraft's navigation system tracks position and velocity, detects when a mascon is affecting the orbit, and fires thrusters to compensate. It's like driving on a road with invisible bumps. You can't see them, but you feel the car shift and you adjust the steering. Mascons tell us about the moon's interior structure. The fact that they still exist means the moon's interior is rigid. If the moon had a thick, molten layer beneath the crust, the dense material would have sunk deeper over time, evening out the gravity. But the mascons remain, which means the moon's mantle is solid enough to support these density differences without flowing. There are also negative gravity anomalies, places where gravity is slightly weaker than average. These exist in some highland regions and older impact basins. The crust is thicker there, and thick crust is less dense than the mantle below. Less density means weaker gravity. The moon's gravitational field is like a topographic map with highs and lows. but made of gravity instead of elevation. Scientists use these gravity variations to study the moon's history. The size and strength of a mascon reveals how much lava filled the basin. The age of the mascon tells us when the impact occurred. Mascons are windows into the moon's past, readable through careful measurement of invisible forces. Even something as seemingly simple as gravity holds layers of information, waiting for careful observers to decode. The moon's interior is mostly cold and solid. It wasn't always this way. When the moon formed from the debris of that ancient collision, it was entirely molten, a ball of liquid rock glowing in space. But small bodies cool faster than large ones, and the moon is small compared to Earth. Its heat leaked away into the vacuum of space. The cooling happened from the outside in. The surface cooled first, forming a crust within a few million years. Beneath the crust, the magma ocean continued to crystallize. Dense minerals sank. Light minerals floated to join the crust. Slowly, layer by layer, the moon solidified. Today, the moon has a structure similar to Earth's, just simpler and colder. The crust is about 30 miles thick on the near side, 40 miles on the far side. Beneath the crust lies the mantle, solid rock extending down about 800 miles. The mantle makes up most of the moon's volume. At the center is the core. The moon's core is small, only about 150 miles in radius. For comparison, Earth's core is about 2,200 miles in radius. The moon's core is mostly iron with some nickel, like Earth's core, but it makes up less than 2% of the moon's total mass. Earth's core is about 30% of Earth's mass. The core might be partially molten at its very center. Seismic data from Apollo missions suggests there could be a small liquid outer core surrounding a solid inner core. But this liquid zone is tiny, perhaps only 50 miles in radius. Most of the core is solid, and all of it is quiet. No convection currents, no movement, just dense metal sitting still at the moon's center. This quiet core means the moon has no magnetic field. Earth's magnetic field is generated by flowing liquid iron in the outer core. The movement creates electric currents, which create magnetic fields. The moon's core is too small and too cold for this process. Whatever circulation might exist is too weak to generate a measurable field. But the moon once had a magnetic field. Rocks brought back by Apollo astronauts show magnetic signatures locked into their structure. These rocks formed billions of years ago and preserve a record of the magnetic field that existed when they cooled. The field was strong, perhaps even as strong as Earth's field is today. This tells us the moon's core was once hotter and more active. Convection currents flowed through liquid iron, generating a dynamo effect. The magnetic field protected the young moon's surface from solar wind, just as Earth's field protects us now. But as the core cooled, the convection slowed and eventually stopped. The magnetic field faded away. The moon's last volcanic activity happened about 1 billion years ago. A few small lava flows created the youngest parts of Oceanus Procellarum. Since then, nothing. The interior cooled below the point where magma could form. The moon became geologically dead. All its internal heat radiated away into space. Now the Moon is a cold, solid sphere with only a tiny warm spot at its core. No volcanic eruptions will ever happen again. No new Maria will form. The Moon's surface is frozen in time, shaped by external forces, like impacts, but unchanged by internal forces. The geology is finished, complete, a closed chapter. Yet the Moon still affects Earth through gravity, still creates tides, still stabilizes our tilt. Its interior might be cold, but its gravitational presence remains powerful. For decades, scientists believed the Moon was bone dry. Every rock sample brought back by Apollo missions showed no water. The intense heat of the Moon's formation should have boiled away any water that existed. The lack of atmosphere meant any water on the surface would evaporate into space. The Moon seemed like the driest place in the solar system. Then, in 2009, everything changed. NASA crashed a spacecraft called L-Cross into a permanently shadowed crater near the Moon's south pole. The impact threw up a plume of debris, and instruments analyzed what came out. They detected water, not just traces, but significant amounts. The Moon had been hiding water all along. The water exists as ice mixed into the soil in permanently shadowed craters. These craters are located at the Moon's poles, where the sun never rises above the crater rims. Some of these craters haven't seen sunlight for billions of years. The temperature in these shadows stays around -400 degrees Fahrenheit, cold enough to trap water ice indefinitely. The ice probably came from comets. Over billions of years, comets struck the Moon, bringing water from the outer solar system. Most of this water evaporated immediately on the hot, sunlit surface. But some water molecules bounced along the surface until they landed in a permanently shadowed crater. There, in the eternal cold, the water froze and stayed frozen. The amount of water is substantial. Scientists estimate there could be hundreds of millions of tons of ice in the lunar polar regions. The concentration varies, but in the coldest, darkest craters, ice might make up 5 to 10% of the soil by weight. That's not a lot compared to ice on Earth, but for the Moon, it's remarkable. This discovery changes everything about future lunar missions. Water means astronauts could potentially live on the Moon for extended periods. Water can be split into hydrogen and oxygen. Oxygen for breathing. Hydrogen and oxygen combined make rocket fuel. A lunar base could become self-sufficient, mining water from the soil instead of hauling it from Earth. The ice also provides a scientific treasure. Each layer of ice preserves the history of when it arrived. By drilling into the ice and analyzing different depths, scientists could learn about the history of comets in the solar system, about the delivery of water to the inner planets, about the chemical composition of the early solar system. But accessing this water won't be easy. The permanently shadowed craters are some of the coldest places in the solar system. Any equipment sent there would need to operate in extreme cold without sunlight for power. The craters are also difficult to see into because they're always in shadow. Landing there would be risky. Scientists have also found evidence of water in sunlit areas, not as ice, but as hydroxyl molecules bound to minerals in the soil. The concentration is much lower than in the shadowed craters, but it exists. Solar wind protons hitting the lunar surface might be combining with oxygen in the minerals to create these hydroxyl groups. The moon might be slowly generating small amounts of water through this process. The dry moon we thought we knew was never completely dry. Water was there, hiding in shadow, waiting to be discovered. The moon still holds surprises, still reveals new secrets as our instruments get better and our understanding deepens. The moon's south pole holds more than just ice. It holds the largest impact crater on the moon and one of the biggest in the entire solar system. The South Pole Aitken Basin stretches 1,600 miles across, nearly the width of the continental United States. It's also the deepest structure on the moon, reaching down about 8 miles below the surrounding surface. The impact that created this basin happened about 4 billion years ago, during the same period when other large impacts were forming the Maria. But this impact was larger than any of those. The asteroid that hit was probably 100 to 200 miles across, more than twice the size of the one that killed the dinosaurs on Earth. When it hit, it struck at an angle, coming in from the northeast. The impact excavated millions of cubic miles of rock, carving out a hole so deep it nearly punched through the moon's crust. In the center of the basin, the crust is only about 12 miles thick. In most places, the moon's crust is 30 to 40 miles thick. The impact came within a few miles of exposing the mantle. The basin floor is lower than any other place on the moon. Standing there, you'd be 8 miles below the average lunar surface. The walls of the basin rise around you, a circular mountain range that took up a quarter of the moon's circumference. The scale is difficult to grasp. The entire basin is so large that if you stood at the center, the far walls would be beyond the horizon. The impact released incredible energy. Scientists estimate it was equivalent to about 1 billion Hiroshima bombs, all detonating in the same instant. The shockwave rippled through the entire moon. The heat melted the impact site and vaporized the asteroid. Rock splashed outward like liquid, some of it thrown completely off the moon into space. What makes this basin unusual is that it never filled with lava like the mare basins on the near side. The impact happened on the far side, where the crust is thicker and the interior was cooler. Although the impact nearly reached the mantle, not enough magma could flow up to fill such an enormous basin. Some small patches of lava did seep through, creating dark spots on the basin floor, but most of the basin remained exposed, impact melt, and broken rock. The South Pole Aitken Basin exposes ancient material from deep in the moon's crust, possibly even pieces of the mantle. This makes it scientifically valuable. By studying the rocks there, scientists could learn about the moon's interior composition and early history. Several proposed missions aim to land in the basin and collect samples. The basin's age and preservation make it a window into the moon's earliest era. The rocks there formed when the moon was young, when impacts were common, when the entire inner solar system was still being swept clean of debris. Those rocks have been sitting unchanged for 4 billion years, waiting to tell their story. From Earth, we can't see the South Pole Aitken Basin directly. It's on the far side, hidden from view. Spacecraft orbiting the moon can map it, photograph it, measure it. but it remains one of the Moon's hidden giants. A scar from an ancient catastrophe that shaped the Moon's structure. And it's just one of many craters that record the Moon's violent past. Every crater on the Moon is a timestamp, a frozen moment from the past, preserved perfectly because the Moon has no weather to erase it. The craters range from miles across down to microscopic pits, and together they tell the story of the entire inner solar system. The oldest craters date back nearly 4 billion years. They formed during the late heavy bombardment, when asteroids and comets filled the inner solar system. This was a violent time, the last phase of planet formation, when leftover debris was being cleared out. The Moon was pelted constantly, sometimes by objects large enough to create basins hundreds of miles wide. You can date a surface by counting its craters. More craters mean an older surface. Fewer craters mean a younger surface that formed after the heavy bombardment ended. The bright highlands are saturated with craters, packed so densely that new impacts can only destroy old craters without changing the overall crater count. These highlands are the Moon's oldest surfaces, dating back to shortly after the Moon formed. The Maria are younger. They formed when lava filled the impact basins between 3.1 and 3.9 billion years ago. These lava flows covered all the craters that existed in those areas, creating smooth surfaces. New craters then began accumulating on the Maria, but there are far fewer than in the highlands. By counting the craters on a mare and comparing to the highlands, scientists can estimate when that lava flow occurred. This technique works because the impact rate has been roughly constant for the past 3 billion years. After the late heavy bombardment ended, impacts became less frequent, but didn't stop. Asteroids still cross Earth's orbit. Some hit the Moon. The rate is predictable enough that crater counts translate directly to ages. Earth was hit just as often as the Moon. We orbit together through the same space, encountering the same asteroids. But Earth's surface is constantly renewed. Plate tectonics recycle the crust. Erosion wears down mountains and fills in craters. Vegetation covers old scars. Earth has only about 190 confirmed impact craters, and most of those are from the past few hundred million years. The Moon preserves what Earth forgot. Every impact that hit the Moon represents an impact that could have hit Earth. The Moon's crater record is Earth's crater record, written on a surface that never erases. By studying lunar craters, scientists learn about the history of impacts in the Earth-Moon system. Some lunar craters have rays, bright streaks of ejected material spreading outward from the impact point. These rays are visible even to the naked eye. Tycho crater's rays stretch halfway across the Moon. Copernicus crater has a prominent ray system too. The rays are bright because they consist of fresh material thrown from beneath the surface. Material that hasn't been darkened by billions of years of space weathering. The rays fade over time. Space weathering darkens the bright ejecta until it blends with the surrounding surface. By looking at how bright a crater's rays are, scientists can estimate the crater's age. Bright rays mean young craters, maybe only a few 100 million years old. No rays mean old craters, billions of years old. The Moon is essentially a museum of solar system history. Every crater is an exhibit. The small ones record the constant rain of tiny meteorites. The large ones mark catastrophic collisions that would have devastated Earth if they'd hit here instead. The moon is leaving, not quickly, but steadily. That 1.5 inches per year adds up. In 1 billion years, the moon will be about 24,000 miles farther away than it is now. In 10 billion years, it could be 240,000 miles farther. The moon that our distant descendants see, if humanity still exists, will be noticeably smaller in the sky. This slow departure has consequences. The most visible one involves eclipses. Right now, the moon and sun appear almost exactly the same size in Earth's sky. The moon's diameter is 400 times smaller than the sun's, but it's also 400 times closer. This perfect ratio creates perfect total solar eclipses, where the moon completely covers the sun's disk, revealing the corona. This is temporary luck, a coincidence of timing in the moon's long journey away from Earth. A few 100 million years ago, the moon appeared slightly larger, and its eclipses lasted longer. A few 100 million years from now, the moon will appear slightly smaller. Eventually, in about 600 million years, the moon will be too far away to completely cover the sun. Total solar eclipses will end. Only annular eclipses will happen, where the moon passes in front of the sun, but leaves a ring of sunlight visible around its edge. We live in a special time. For most of Earth's history, the moon was closer and appeared larger. For most of Earth's future, the moon will be farther and appear smaller. Right now, we're in the narrow window when the sizes match. It's pure chance that intelligent life evolved during this window, able to witness total solar eclipses. The moon's departure also means tides will gradually weaken. As the moon moves farther away, its gravitational pull decreases. The tides will still exist, but won't rise as high or pull as strongly. Coastal ecosystems that depend on tidal rhythms will have to adapt to these slowly changing conditions. Earth's day will keep getting longer too. The moon's gravitational brake continues working, slowing Earth's rotation. In 1 billion years, a day might be 25 or 26 hours long. In 2 billion years, perhaps 27 hours. The change is slow enough that life will adapt easily, but it's real and measurable. If given enough time, about 50 billion years, Earth and Moon would reach a final locked state. Earth's day would equal a lunar month, both lasting about 47 current days. Earth would show only one face to the Moon, and the Moon would hang stationary in the sky above one hemisphere. The other hemisphere would never see the Moon at all. But this won't happen. The Sun will die first. In about 5 billion years, the Sun will exhaust its hydrogen fuel and begin fusing helium. It will expand into a red giant, growing large enough to potentially engulf Earth's orbit. Even if Earth survives, barely, the Moon will be vaporized or ejected. The Earth-Moon system will end long before reaching tidal equilibrium. For now, the Moon continues its patient journey outward. Each year, a little farther. Each century, a little smaller in the sky. The process is so slow that no human will ever notice the change, but it's there, constant and inevitable. The Moon that guided our ancestors is slowly leaving, moving away into the darkness of space. Pulled by the same gravitational forces that created it. But tonight, the moon is still here, still close enough to light the darkness, still pulling gently on the oceans, creating tides that have risen and fallen for billions of years. The same moon that shone on the first life crawling from the seas. The same moon that lit the path for ancient travelers. The same moon hanging quietly above you now. Every human culture has looked up at it with wonder. The ancient Babylonians tracked its phases to create the first calendars. The Polynesians navigated by it, crossing thousands of miles of open ocean. The Greeks saw a goddess riding across the sky. The Chinese saw a rabbit making medicine. Different stories, same moon, same sense of awe. The moon has been part of our lives for as long as we've been human. It marked time before we had clocks. It lit the night before we had fire. When our ancestors first looked up and wondered what that bright disk was, the moon was already 4 billion years old, already ancient beyond comprehension, already carrying the history of Earth's formation in its rocks and craters. We've walked on it now, left our footprints in its dust, brought pieces of it home, but it remains mysterious in many ways, still teaching us about the solar system's past, still revealing surprises like hidden water ice, still asking questions we haven't yet answered. The moon shaped our world in ways we're still discovering. It gave us stable seasons. It slowed our rotation. It created tides that helped life transition from sea to land. It lit the night for millions of years before humans invented artificial light. Without the moon, Earth would be a different planet, and we might not exist to look up at it. Right now, while you rest, the moon continues its work, pulling on the oceans, moving slowly away, keeping Earth's tilt stable, reflecting sunlight down to Earth's night side, doing what it's done for 4.5 billion years, patient and constant. The moon is a reminder of timescales beyond human comprehension. It's been there longer than life on land, longer than complex life in the oceans, longer than Earth has had a solid crust. It will be there long after we're gone, continuing its slow spiral outward, pulling itself toward a future it will never reach. But for now, in this moment, the moon is ours to wonder at, close enough to see details with your bare eyes, close enough to cast shadows, close enough to create perfect eclipses. We live in a special time when humans can look up and see not just a distant light, but a world we've visited, touched, and understood a little better. Before you settle into sleep, I want to invite you to join this community of peaceful minds. If tonight's journey through lunar science brought you calm, if learning about the moon helped quiet your thoughts, please subscribe to Simple Science for Sleep. Tomorrow night, we'll explore something equally wonderful, maybe the quiet mystery of how stars are born, or perhaps the gentle story of how mountains rise from the sea. There's always another corner of science waiting to help you rest. And I'd love to hear from you. Leave a comment telling me what surprised you most about the moon tonight, or simply share where you're watching from and what brought you here. Every comment reminds me that we're all in this together, finding peace in curiosity, using wonder as a bridge to sleep. Hit that like button if the moon story resonated with you. It helps others find this quiet space too. People just like you, lying in bed, looking for something calming to think about as they fall asleep. Your simple click connects them to this community. Rest well. The moon will still be there tomorrow night and the night after, continuing its eternal dance with Earth. Sweet dreams.